In this video, we're going to introduce what we mean when we talk about the order of an element and then introduce the concept of something called cyclic groups. So far, I think at least I've mentioned the order of a group, but when we're talking about the order of a group, we just mean the number of elements in the group. Now, this word order gets used in two different senses, but there's a reason because they're definitely connected. So when we're talking about the order of an element, then what we mean is that the order of an element G is the smallest power which we can raise that element to in order to get the identity element, which we're normally going to refer to as E. So I know I've said power here. I really mean doing the element to itself k times, because if additions are the operation for our group, then it might be adding itself to itself k times, and we probably wouldn't use the power notation. But our power notation is going to be the standard in any other scenario. So there's a few examples I want to look at because this is quite an abstract definition. I feel it starts to make more sense when you look at some examples. So the first example I want to look at is actually taking the example from our last video where we looked at the symmetric group for an equilateral triangle. So we had these elements here. Now, we've got our identity element E, that's the do-nothing transformation here. If we look at, I'm going to look at the reflective transformations first here, which are S1, S2, S3, where we're just reflecting in a line. If we do S1, S1, then we get our identity straight away. So we're saying here, if we do S1 squared, we get our identity element. So that tells us S1 has an order of 2. Similarly, S2 gives an identity element. So S2 squared is equal to E. So this also has order 2. And S3 also has order 2. Whereas, so R1 and R2, which were a rotation, so R1 was a rotation 120 degrees anti-clockwise, R2 was a rotation 120 degrees clockwise. If we do R1, R1, we end up with R2. So R1 to the 1 is obviously just R1. R1 squared was equal to R2. Now, R1 cubed, we're then doing R1 times R2, which is equal to E. So because R1 to the power 1 definitely wasn't the identity, R1 squared still wasn't the identity, but R1 cubed is the identity, we'd say that R1 has order 3. Now, if we think about geometrically what's going on there, that should make complete sense. If you think about taking a triangle and rotating it by 120 degrees, you're going to have to do that 3 times before you get back to having done nothing overall, which is the identity that we want. So that's a kind of more intuitive sense of what we mean by the order of an element here. Okay, let's look at some non-geometrical examples now, because we've done lots of geometry in the last couple of videos. So what about if instead we consider, I'm going to say we're going to take the group with the elements 0, 1, 2, 3, 4, 5. Sorry, I should make sure I've got sign notation at the end there. And the operation I'm going to consider, I'm considering under addition modulo 6 here. So as in, so when we add the remainder after we've divided by 6 here. Now, the first thing we should note, even before so I want to think about the order of each of these elements. But the first thing we should note is, well, which one's the identity? Otherwise, we're not going to be able to find the orders at all. What can we add which has no effect? Well, because that's going to be our identity, that's 0. Because 0 plus any element is just our same element. So 0 is identity. And this would mean that it has order 1, because we don't, as soon as we start with 0, 0 to the power 1 is 0, we're done here. Now, the order of 1, let's think what happens when we do 1. So we'd start with, so this is where our power notation is a little bit confusing, because I want to say 1 to the power 2. I really mean 1 plus 1, and then 1 plus 1 plus 1. So when we start with 1. The next time if we do 1 plus 1, we get 2. If we do 1 plus 2, we get 3. If we do 1 plus 3, we get 4. 1 plus 4, we get 5. And then 1 plus 5 modulo 6 gives us 0. So, well, what we had to do here, we've had, this was really 1 to the 1, 1 squared, 1 cubed, 1 to the 4, 1 to the 5. And this was 1 to the 6. So we had to add 1 6 times to get to our identity element here. So 1 has order 6. What about the order of 2? Well, if we think about going from 2, starting with 2, 2 plus 2 gives us 4, plus 2 again, we get 0 modulo 6. So 2 has order 3. The order of 3, we just go 3, and then, oh sorry, I wrote 6, I really should have wrote 0 there. But 3 plus 3 gives us 0 modulo 6, so 3 has order 2. And then the order of 4, we're going to do 4. 4 plus 4 modulo 6 is 2. And then 2 plus 4 modulo 6 is 0. So 4 has order 3. And then 5, this one's a bit weird. So 5 plus 5 is 10, which is 4 modulo 6. Plus 5 again is 9, which is 3 modulo 6. Plus 5 again is 8, which is 2 modulo 6. Then 1, and then 0. So 5 also has order 6. Now, there's something special about this group here, and before I mention that, I just want to flag one thing. Hopefully, you might notice here that all the orders of all your elements here are factors of 6, and the order of your group here, the size of your group, was order 6 because it had 6 elements in your group here. That should always be the case. We're not going to prove it yet. We will touch on it later on in the course. So if you ever get an element having an order that's not a factor of the order of your group, they'll pause, something's gone wrong. Now, like I say, something special is happening here. If we look at 1, it has order 6. As we went through 1, we generated every single other element of the group, and we cycled through the whole group, and it would just keep cycling if we kept adding 1 here. So for that reason, 2 words that we're going to use, we're going to say 1 is a generator of the group. It generates all the other elements just by itself. And we're going to say this whole group is a cyclic group as a result. There was one other generator here, though, and that was 5. Because look, if we started with 5, we start with 5, then we generated 4, then we generated 3, then 2, then 1, then 0, just by keeping on adding 5. So 5 is also a generator. The way of finding generators, a generator of a group will always have the same order as the group itself. These had order 6, and the group had order 6. So these are 2 definitions we want to know. So an element is a generator. If the order of the element is equal to the order of the group. To the order of the group, and then if we have any element like that, then we're going to say the group is cyclic. So if a group has a generator, it is cyclic. I want to just look at one more example of a cyclic group and see if we can find the possible generators of that group. So the next one I want to look at is I'm going to take the group, the set containing 1, -1, I, and -I under multiplication. So in this case, we're looking for elements that have the same order as the group. The group has order 4 because it's got 4 elements here. Now, again, before we want to start thinking about the orders of elements, we need to decide what our identity is. Hopefully, we can spot straight away. Now, under multiplication, our identity is definitely 1. Multiplying by 1 is what gives us, what doesn't change any other element here. So let's see whether we can find a generator. If we started with -1, if we did -1 squared, we'd just go 1 straight away. So -1 would have order 2. Whereas if we start with I, so I to the power 1 is equal to I squared is equal to -1, I cubed is equal to -I, and I to the 4 is equal to 1. So I has order 4, and I is a generator. So really useful to look out for these cyclic groups. We're going to start, I know last video, I touched on isomorphic groups, this is going to be really useful because we're going to get lots of cyclic groups appearing, and it makes finding group isomorphisms very easy. But that will be the next video where we'll really get into that there. So in general, what do we mean and how can we present a cyclic group? So in a general case, any cyclic group can be written in the form E, where E is identity, and then a generator G squared, G cubed, all the way up to, so here, a cyclic group of order K, I'm going to say, of order K just involves finding a generator G and then doing G up to the power of K minus 1, and then G to the K would be equal to our identity there. So this is what any cyclic group of order K looks like. And you can find, for any value of K, you'll always be able to find a cyclic group of that size. Next video, we'll start looking at these isomorphisms.